We're going to balance this using the algebraic method. First, put in variables A, B, C, and D because we have 4 chemical species. Then set up linear equations accounting for each element type, accounting for the quantity of each element type. Your equal sign for your linear equation occurs at the yields or produces arrow. There are 2 sodiums associated with A and 1 associated with C. Oxygen is everywhere. 2 associated with A, 1 with B, 1 with C, and 2 with D. The hydrogens, 2B equals 1C. You're going to select one of your coefficients. You're going to select one of your variables and set it equal to 1 and solve for the rest. The best ones to choose are the ones with the highest coefficient in the linear equation and occur in the most locations. Both A and B are equal to 1C. This would have told us that A and B are equal, and so choosing A or B wouldn't have mattered. D, while it has the same high coefficient of 2, would not have been a good choice because it doesn't immediately tell us about one of the other variables. Eventually, we'll be able to solve for D. When we do so, we find out that D equals a half. Since we're not allowed to have halves, because everything must be the simplest whole number ratio, we will double everything. The algebraic method still allowed us to solve for everything. with little to no trouble. Next, we're going to solve the more traditional way, which is a trial and error, seesaw, teeter and totter, back and forth method. In doing this method, oftentimes people create what is referred to as a RAP table, a count of the reactants, a list of the atoms present, and then the products version of it on the right side. This will allow you to see what is equal and what is not, the things that are balanced already and the things that are not. You can then approach it trying to balance everything. In this case, we were trying to balance the sodium. So we put a 2 down, and it doubled practically everything. The oxygens did have to get recounted. We then went after the oxygen. The oxygens were at odds with each other, so we had to make an adjustment. We then had to make a further adjustment of the sodiums. Make a further adjustment of the sodium hydroxide because of the oxygen and the hydrogen content. That affected our nitrogens. That affected our sodiums, and so we had to adjust there as well. The teeter-totter method is not recommended as this sort of thing happens, and sometimes people get rather confused. To show you that the RAP table and the linear equations are effectively the same, we're going to go ahead and put both of them down side by side. You can see that while things like oxygen may occur in multiple locations, when you add them up in the linear equation, you will see, based off of the coefficients that are in the linear equation, that they are the same as the RAP table count. Because of the variables and the equal sign, and the fact that, like oxygen, they can be split up and separated on various sides, this can throw people. But realize they are the same.